Good morning, everyone. I'm happy to be here and present our paper, Enhancing Network Attack Detection with Distributed and In-network Data Collection. This work is a joint collaboration between University of Central Florida and Ewha Women's University. Here is the outline of the presentation. Network traffic measurement is crucial for various northbound security applications, including provisioning, fingerprinting, and anomaly detection. With the rise of the AI, these applications are leveraging its power to boost their performance. However, to ensure the success of the AI, we need to maintain high data availability, which is a challenging task. To see why it is challenging, let's see how the data is provided to these applications. Basically, cloud-based defense, they are using BGP DNS technology to redirect the customer traffic to a dedicated data center with abundant resources for data collection and further analysis. However, their focus is only on the customer traffic. Basically, they are neglecting the collection of traffic for non-endpoint attacks, such as attacking the infrastructure. So in that sense, we call this approach as weak data availability for security machine learning application. On the other hand, we have ISP-level defense, which basically, with the direct access to the in-network infrastructure, provide full data visibility. However, the collection of data in raw format and its migration from infrastructure layer to the application layer introduces a huge bandwidth bottleneck. And this bandwidth is usually reserved for latency-sensitive network operations, such as updating the policy. So in that sense, we call this approach as weak data availability. Obviously, with the expansion of the network for data collection, it's not feasible to just collect all the data in a centralized location. Now the question we are asking, can we provide a strong data availability by removing this bottleneck? And the answer is yes, we can, which is the focus of this work. Basically, simply put, the idea is to process the data where the data it is generated. And instead of sending the raw data to the data center, we are sending the processed data to the data center. Although this model provides a strong data availability, its realization it's not straightforward because of basically the main challenge is the resource constraint of the current hardware switches. As a solution, we are introducing in-network serverless data collection. Basically, ISDC is a middleware, and it resides between the infrastructure layer and application layer. And its goal is to create a data layer. In the switches data plane, ISDC collaboratively measure the network traffic while simultaneously keep synchronizing and aggregating the data in the local switches control plane through the PCIe communication channel. Basically, this design, we want to support machine learning-based security application with high-quality data. To realizing ISDC, there are some key challenges that we need to tackle in current distributed measurement schemes. Basically, current distributed measurement schemes are twofold. The first one is remote decision making. Basically, they are using the global view of the network for resource optimization and resource allocation for the task. But basically, the downside of this approach is the slow adaptation to the dynamic shift of the traffic. So in that sense, they are not using the resources efficiently. On the other hand, we have on-site decision-making, which solves this slow adaptiveness through the local view of each switches for decision-making. But the problem is that the lack of efficient collaboration and even the local view of the network creates another problem, which we call it the duplicated task measurement. And basically, it's waste resources from that aspect. Also, there is another problem which relates to the local view decision-making, and it's about the creation of fragmented data. Basically, for a single flow, the data can be measured in multiple switches in inclusive or exclusive timeline. And later, in our experiments, we found that if we are using this data as a source for distributed learning, the presence of the fragmentation will lead to model poisoning. It confuses the model for the prediction. And recall that we don't want to send the data in the centralized collection. So we want to do it in the network itself, process the data in the network itself. To resolve this issue, we have three main design goals. Basically, for the resource constraint of the hardware switch, we want to enable the effective resource utilization. according to the security application demands. The second design goal is a dynamic task allocation to enable efficient task coordination. We want to maximize the network-wide resources. And the third one is to providing reliable data source for security. We want to ensure data integrity and eliminating model poisoning caused by data fragmentation. Now let me introduce you the ISDC framework. In the data plane, we have two main components, named flow identifier and feature meter, which are the two hash table-based data structure. In the control plane, we have a general purpose CPU with abundant DRAM. For a set of flows that enters the network through the H switch, let's say here S1, FI first inspect those flows to identify the interested flows for the machine learning applications. And then the identified flows will be measured collaboratively in the following FM in the flows routing path. Whenever applicable, we are collecting the features for inactive flows in the switch's local control plane. We have a data migration protocol for removing the fragmentation and in-network aggregation of the data in the flows edge switch. And with the collected data, eventually each switch has created a local models, which leveraging the distributed learning technology, they aim to share the knowledge for the creation of a global model. So in that sense, they only need to send the parameters through the northbound links. Now I will delve into each design in more detail. Recall that the first design was about effective resource utilization. And our statement is that even though we are using the distributed switches resources for traffic measurement, still achieving the full flow coverage is not feasible, basically, with every day the traffic is increasing. As a solution, we are suggesting application-focused task prioritization in favor of large flows for the machine learning application. Basically, the idea is that MLDL, there are disfavoring sparse data point, and basically they are created by supervised flow with only 1 or 2 packets. And for that, we have FI, flow identifier. It's a real-time large flow prediction data structure, and basically we are reducing the complexity from ON to O1. And with this design, we aim to relax the data plane competition for the more task allocation of the interested flows for the machine learning. And in that sense, we are reducing the resource wastage for the small flows data collection. To enable the efficient and basically network-wide collaboration, the idea is that we want to have more task migration based on the switches resources. But when we are doing the task migration, the collected data so far, we are not migrating it to the task. We are keeping it in the switches local switches control plane. To make it, basically, the idea is to make it more dynamic and save resources. And this task migration protocol follows a hybrid policy with 2 opposing strategies. One is to maximize the resource utilization, another one to minimizes the migration footprint. And basically, this design is to enabling efficient network-wide collaboration to increase flow coverage. And we have a data migration protocol, which removes the fragmented data through in-network data aggregation. Basically, this protocol follows a non-blocking mechanism for data delivery and acknowledgement, and it does not require prior knowledge of the topology or routing paths. And basically, with this design, we want to remove the incomplete data, aggregate them in the network itself, and providing high-quality data for the machine learning. Now, I will talk about the main experimental result. We have the prototype of ISDC in BMV2 software switch. We are using Mininet as our simulation environment. We also have the hardware prototype in Intel Tofino 1. We are using 3 real-world ISP topology, a small, a medium, and a large one, with spanning from 18 to 116 switches. And we have 2 security use cases, covert channel and DDoS attack detection as an application of our system. For security use cases, we are using the small topology with 18 switch, 25 links. And we configure the switches to collect features from traffic for both attack and benign. The data basically measured in and aggregated in distributed manner. Then the distributed data later they're following a standard federated learning for creation of a global model, and the global model is decimated to the 18 switches for attack detection. Here, we are using standard federated learning, and basically we want to study the capacity of each measurement scheme to support the machine learning, but the capacity of FL here is not our interest. And here is the result for the security application. Strawman here, what we mean is the lack of collaboration. The switches just measure whatever they can. CSAMP, NSP are the two remote decision-making. They are looking into the global view of the network, and CFS is the state-of-the-art decision-making for the local view of the switch. And what we achieved is 94.1% flow coverage and 0% data fragmentation. We are only wasting 8% of the memory for small flows, for untargeted small flows for the machine learning. And WMRE here is the measure of data quality, closer to 0 the better it is. And with this high quality data, what we achieved 96% F1 score and 93.8 AUC in the first single round of federated learning, basically our convergence port for covert channel detection. And when we compare it to the 10 round of federated learning, the convergence point for other schemes, we found that ISDC has even the potential to reduce the computation for training. Later, we did the experiment again, but this time with the CFS, the winner of the covert channel, and the trend is pretty similar. 93.1% coverage, 0% fragmentation, better quality data, and basically it's resulted to the 80.9% F1 score and 94.5 AUC in 10 round of federated training. Also, we manually removed the fragmented data, the duplicate data created by CFS. We found 14% improvement in F1 score, which verifies the presence of incomplete data cause model poisoning. And to further study, we used our large scale topology with 161 switch, 328 links. Here we are using 8 minutes of KDA, 14.5 million flows, 215 packets, and we are using flow coverage, WMRE as measure of data quality. But we achieved consistent delivery of full data coverage for top 500K flows and higher data quality, basically the guarantee of ISDC for data collection compared to the current schemes. In conclusion, we talk about the limitation of existing framework in terms of resource wastage, fragmentation cause model poisoning. As a solution, we talk about ISDC, we propose ISDC, and with 3 design goals. And what we achieved is high coverage and quality data collection, and resulted in enhancing data availability for machine learning, deep learning application. We have our source code in the GitHub repository. Thank you for your attention.